Okay, 2.1, functions and equivalent algebraic expressions. So we're going to take a look at the different ways that we can tell if algebraic expressions are equivalent. Okay, so in order to determine this, number one, simplify both expressions to see if they're algebraically the same. Okay, and then this just proves that they're the same. Okay, additional methods that are used to suggest but not prove that they're equivalent are check several points, okay, to ensure that there are similar points. However, this doesn't prove that they're identical or like equivalent, because if you check a couple points, you have to check every single point, okay, and we can't humanly do this, okay, and then graph the two functions, so to identify if they yield the same graph. Again, there may be parts of the graph that we can't see, and at that point, it's ineffective, okay? But these two suggest that two expressions are identical, okay, or equivalent, but algebraically is the best. Okay, so example one, determine whether the functions in each pair are equivalent by first testing three different values of x. So we're going to test -1, 0, and 1. Then we're going to simplify the expressions on both sides, and then we're going to graph them. So we're going to do all three. Okay, so remember function notation. We're going to sub in f at -1, okay, and our f function is here, our g function is here. Okay, so 2, -1 minus 1 squared plus 3, -1 minus 2. Okay, so we have 2, -2 squared plus -3 minus 2. If we keep going down, we're going to get the answer of 3. Okay, what about g at -1? Well, 2, -1 squared minus, remember to bracket the -1. Okay, so 2 times 1 plus 1, we also get 3. Okay, f at 0, 2, 0 minus 1 squared plus 3, 0 minus 2. Okay, so 2 times 1 plus -2. Okay, what about g at 0? 2 times 0 squared minus 0. Again, we get 0. Okay, and the last one, f at 1. Again, if you sub in the 1, we're subbing into every single time where we see an x. 1 minus 1 squared, so that's all going to be 0, plus 3 times 1 minus 2, and we get 0 plus 1, which is 1. Okay, what about g at 1? 2 times 1 squared minus 1. Okay, we get 2 minus 1, which is 1. Okay, so the first way, when we take a look at a couple different points, we get, for -1, we get 3 each time. For 0, we get 0 each time. And for 1, we get 1 each time. Okay, now, we're going to algebraically do this. So, what I'm going to do is I'm going to completely expand the left side here. So 2, and then x minus 1 squared. What we would do is we would write it twice and expand. And then we can add 3x minus 2. We no longer have to put this in brackets because there's a plus sign before. Okay, let's check if this is equivalent to 2x squared minus x. So when we expand this, we get x squared minus x plus 1 plus 3x minus 2. Okay, now let's expand the 2 into the bracket. So we have 2x squared minus x minus 2x minus 2x plus 2 plus 3x minus 2. Okay, now let's collect like terms. We get 2x squared minus 2x is -4x, and then plus 3, we're going to get -x. And then the positive 2 and the -2 cancel out. So algebraically, these two functions are equivalent. Okay? Now graphically, if we were to graph -1, 3, 0, 0, and then 1, 1, both graphs are going to look like this. Okay, you can also use Desmos.com and sketch on the graphs f at x and g at x. Okay, and therefore these equations are equivalent. Okay, let me bring up Desmos and we will put them in. Okay, so here's Desmos. I'm going to start typing these in. 2, we have x minus 1 squared plus 3x minus 2. Okay, and the next one, 2x squared minus x. So as you can see, the blue and the red, you can't actually see the red because they lie on top of one another. So they are equivalent. Okay, again, we're going to do the same 3 steps. So first we're going to sub in -1, 0, and 1. Okay, I chose these numbers because they're honestly the easiest numbers. Okay, so we have 2 functions here, x squared minus 2x minus 8 over x squared minus x minus 12. Okay, and then we have g at x, which is x plus 2, x plus 3, over x plus 3, I should say. Okay, so let's go ahead and sub this in. So -1 squared minus 2, -1 minus 8, all over -1 squared minus -1 minus 12. Okay, and if we break this down, we actually get 1 plus 2 minus 8 over 1 plus 1 minus 12. We actually get an answer of 1/2. Okay, so we get -1 comma 1/2. Now let's see if g at x is the same for -1. -1 plus 2 on the top, -1 plus 3 on the bottom. And yeah, we get 1/2. So that one works. Okay, what about f at 0? So 0 squared minus 2 times 0 minus 8. Okay, all we're doing is plugging in the 0. 0 squared minus 0 minus 12. Of course, those all are nothing. So we get -8 over -12, which gives us 2 over 3. Okay, so let's double check with g at x, or g at 0, if it gives us 2 over 3. Okay, 0 plus 2 over 0 plus 3, and we get 2 over 3. Okay, now f at 1 equals 1 squared minus 2 times 1 minus 8 over 1 squared minus 1 minus 12. Sorry, this is squared. It's not a 1. It's not a 2. Okay, I get -9 over -12, which gives me 3 over 4. Okay, so this point is 1 comma 3 over 4. Now g at 1 equals 1 plus 2 over 1 plus 3, so we get 3 over 4. Okay, so just taking a look at a couple random coordinates, we can see that these look equivalent. Now let's actually prove this algebraically, and this is the only real way of proving this, okay? So in order to prove that these two are equivalent, why don't we factor the top and the bottom here? So what two numbers multiply to -8 and add to -2? Okay, well, -4 and 2. So the top factors to x minus 4, x plus 2. Okay, and for the denominator, what two numbers multiply to -12, add to -1? I get 3 and 4, and the negative is going to be on the 4. So x minus 4, x plus 3. Okay, so we get x plus 2 over x plus 3. Okay, x minus 4's cancel, and then these two algebraic expressions are equivalent. On both sides, we get x plus 2 over x plus 3. Okay, I'm going to show you how this looks. So on the bottom, this is going to be a vertical asymptote. Okay, so x is not going to equal -3. Okay, and then we have the horizontal asymptote at y equals 0. Okay, and this graph's going to look like this. And we can double check this on Desmos. Okay, so we have on the top x squared minus 2x minus 8 over, and then bracket them so that the numerators group and then the denominators group, minus x minus 12. Okay, so this is our blue graph. And then we have x plus 2 on the top over x plus 3. Okay, so these definitely look equivalent here too. Like the blue graph and the green graph, okay, they lie on top of one another. Okay, I'm going to tell you one thing though. Algebraically, and we're going to get into this, if we take a look at these two, let's do this in another color. There we go. Okay, this denominator versus this denominator, we actually have two restrictions here. So x cannot equal -4 and x cannot equal -3. Whereas in g at x, we can just have x cannot equal -3. Okay, so that's called a restriction. And because because f at x actually has an additional restriction, and it's going to be at -4, so wherever it lies here, right? These two are actually not equivalent. Not equivalent. We wouldn't be able to tell that by plugging in points, and we wouldn't be able to tell that by graphing it, but algebraically we can tell because of the denominator. Because f at x has an additional, we call it a restriction, and we're going to get into that right now. Okay, so when we talk about determining restrictions, we do so on rational expressions. So what a rational expression is basically just a fraction, okay? So there's one expression in the numerator, and then it's over another expression, okay? And the bottom expression obviously can't equal 0. This is where we get our restrictions from. So we determine restrictions by stating the values of the domain that are not defined. For rational expressions, we cannot have a denominator equal to 0, as these values are not defined. Okay, the example, the expression 1 over x plus 2 has a restriction of -2, since in this denominator, if we did -2 plus 2, we would get 0. Okay, and we cannot divide by 0. So example 2. Simplify each expression and determine any restriction on the variable. So let's factor the numerator. What two numbers multiply to 21 and add to 10? Okay, well, it's going to be 3 and 7. So the numerator factors to x plus 3, x plus 7. Now the denominator factors to x plus 3. Okay, so to simplify, we cancel those out and we get x plus 7. However, because the x plus 3 at one point in time was in our denominator, we have to write a restriction. Okay, so we know that x plus 3 cannot equal 0. So when we bring this over, x cannot equal -3. So our domain is x is an element of the real number system such that x cannot equal -3. Okay, next one. So what two numbers, we're going to factor again, multiply to -30 and add to -7. Okay, so if we list the factors of 30, 130, 215, 310, 310 is going to subtract to 7, and we have, let's go -10. Okay, so I'm going to actually do this on the side of my paper and then insert it here. So 6x squared minus 7x minus 5. Oh, I'm going to just break down that 7x right into 3x minus 10x minus 5, and then factor by grouping. Okay, so 3x can come out of the first two terms, and -5 can come out of the last two terms. So 3x, x minus 1, and -5, 2x plus 1. There we go. So I get 3x minus 5 as one bracket, 2x plus 1 as another bracket. Okay, 3x minus 5 and 2x plus 1. Okay, now for the denominator, what two numbers multiply to -10 and add to 1? Sorry, multiply to, -30 again, add to 1. Well, we can take the same factors, 130, 215, 310. I'm going to go 5 and 6. Okay, so 5 and 6, and we're going to have a negative on the 5. So let's take this 3x squared minus 5x plus 6x minus 10, and we're going to factor by grouping. Okay, only an x can come out of the first two terms, so we're left with 3x minus 5. And in the last two terms, I can pull out a 2. So plus 2, 3x minus 5. Okay, so we get x plus 2, 3x minus 5. Okay, so in this case, we can cancel out the 3x minus 5's, and we are left with 2x plus 1 over x plus 2. This is the simplified version. Now, back to restrictions. If it was ever in the denominator, we have to write a restriction on it. So 3x minus 5 cannot equal 0, and also x plus 2 cannot equal 0. Okay, this one's easy because it's basically just like the opposite. So instead of 2, it's -2. But when the coefficient here is not 1, it's going to be a little bit more difficult. So let's do 3x cannot equal 5, and then divide out the 3. Okay, so x cannot equal 5 over 3. So we have two restrictions here. So if we were to write out the domain, x is an element of the real number system such that x cannot equal -2 or 5 over 3. Okay, example 3, a square with side length 5 centimeters. Okay, so we know squares look like this, where all the sides are the same. Okay, so 5 centimeters each side, is removed from a square of side length x. Okay, so there's a bigger square here, and it's going to be x. So this one's removed, so we take this one away. Okay, so sketch the situation, so that's good. Now express the area of the shaded region as a function of x. Oh, so it won't be this one as a shaded region. It would be this one, like what's left over. Okay, so again, this is A. B would be, area equals, like the area of the entire square, which is x squared, minus 5 squared. So in other words, x squared minus 25. Okay, write the function in factored form. So if we were to factor this, this is difference of squares, has two terms, and both of these can be rooted. So this is factored to x plus 5, x minus 5. Okay, now D, what is the domain of the area function? So when we consider solving for the x's here, we get x equals -5, and then x equals 5. Okay, so the -5 is inadmissible. That means that the domain has to be greater than 0. Okay, so if the length of the width is less than 0, then there's not going to be any area. So the domain on the area, or on the x's, is x is an element of the real number system such that x is greater than 0. Oh, let's go. And then it's going to max out at 5. 0, to 5, and it has to be strictly between these two numbers.